Official welcome to lecture number 10, I believe it is. And we've been talking about the relativistic field equations. So these are supposed to be equations that have the same form for all inertial observers. That's the trouble. And some equation, you just come up with something and then it isn't the same for all. So we had to think about Lorentz transformations, and that's what we prepared last week. And yesterday, we talked about the scalar field. We came up with the Klein-Gordon equation. I can write this again, Klein-Gordon. Yeah, I have to start with it. It is the Weyl operator. There's so many ways of writing it. Let's write it in the most complicated. Let's write it in the most complicated way. So you have two indices that transform as a vector, and then you contract them together by this thing, and then you make a Lorentz invariant scalar out of it. And if you wanted, you can add another Lorentz invariant scalar, and it still makes sense. And this is a mass term which has these three factors to get the dimensions right. So this is our Klein-Gordon. You knew that, but we still played the story to come up with this equation. And then we were talking about Weyl spinors. These are two, so you have two choices. They are chiral, so you can have a representation. Well, this is the representation 0, 0. You can have 1/2 0 or 0 1/2. And we focused on the first one, and the first one we will call psi L, and L stands for left chiral, and it is a spinor, so it has two components, psi 1 and psi 2, and we were looking for an equation for this. And if you start with one derivative, like this, it's too restrictive because it sets both components to a constant. And we had this here too, and we had to do some extra index and some subtraction. But here, there is this index, which usually isn't written. We can introduce an index if you wanted, and say A is 1 and 2, and then we have an index there. And we can do something with the mu and the eta. This is the mu and the A. So we need some object like this. It's certainly not this guy. But this is what we are about to figure out. And then set it to 0. With some thing that actually can contract the two. Okay. And how do we do this? We look at the transformation of this combination, psi L dagger and psi, and we saw that under rotation this is the scalar. And then we looked at psi dagger L sigma k in between a vector, also like a vector, like this. So this vector is the Pauli matrices together. And so this list of 4 entries transformed in a nice way. This is a scalar under rotations, this is a vector under rotations, so I write this one, writing it like this, and then we thought maybe the whole thing is a 4 vector, so it's some W, and then the question remained, well, is it really 1? And if it was 1, is it upstairs or downstairs? Is it covariant or contravariant? It turned out by looking at a boost that it transforms with the inverse Lorentz transformation, with the inverse lambda, and that means it is a covariant one, and that made us, let us do this definition, made us define a Pauli 4 vector with these components, with the 1 and the sigma vector here. And then this whole thing can be written as psi sigma mu psi L. My dagger sigma mu psi L. And right. Seeing that this is the 4 vector, it was a little sketchy. I expanded only to linear order. I only looked at the boost in the 3 direction. And now I have pulled up my Mathematica file where we do this now completely, so just that you're happy. And what do we want to prove? So I want the transformation of this thing. How does this thing transform? Psi L dagger. So the psi L sort of this UL psi L, right? This is the definition of it. And the U, let's write the UL first. And UL. I don't like that this blackboard is so dirty, I don't even see what I'm writing. Psi L dagger sigma mu psi L transforms under now anything rotations or boosts into psi L dagger UL dagger. The sigma is the sigma, and this is the UL psi L. And now the claim is that this is lambda. What have I done? What? Are you just too polite? Because I was talking about this is a lower index, and now I came up with this upper index, and this is an upper. This equation doesn't make any sense. Don't be polite. Like it's not the right politeness. Just tell me that I'm doing nonsense. So I did claim this is a lower it's a covariant vector, and that's true. But somehow here so we have to have some bottom thing. This needs to be the bottom thing, exactly. So goes here. Now it's better. Except for people call this Pauli matrix not sigma, but sigma bar. There's nothing's happening here. It's just a different symbol. You could call it tau or anything. But this is standard. It's also Pascal-Schroeder notation, which I try to stick to. It'll only become clear later why we had to have a bar. Okay, let me tell you now. We looked at the left chiral story. If we had discussed the right chiral story first, we would get similar things, and then they called the sigma mu without the bars, like the first thing. Then you have the sigma without any fancy decoration, and then you move on to the left-handed one, and then you see, oh, I get something that's not exactly the same, similar. So I want the sigma, but the sigma is already used, so I use the sigma bar. Since I'm coming backwards from the left-hand side, still wanting to stick to the notation, I have to put the bar here, and you wonder why, because there will be later sigma without a bar. We do the left-handed side because left is our world. We have left chiral particles in this world. Now we know right. That's what our universe actually do. Having fixed this now, I noticed here, because here was suddenly didn't make any sense with my anything now. I'm claiming this is now a lower index, so this needs to be mu psi L dagger sigma bar mu psi L. So this is the claim that this is correct. Now I'm picking out this part. Great. Rip off the spinors. Now watch. First, here there's a bunch of definitions. You could do this simpler. This is only to write what is the generator JX matrix form, and a little bigger, please. Where's it gone? So here, this is now I all of the above is just to get the explicit form for these generators. Which one do you want? KX, it's this one, KZ, so they're defined. Now we've moved the chunk. Hello. Here. Now, this is the sigma bar up. Sigma bar up is the, oh, we want down. Sigma bar down, dn is down. Sigma bar down 0 is the identity matrix. Sigma bar down with the 1, 2, 3 is the Pauli matrix 1, 2, 3. So execute. And then I'm defining the UL. And here I have the whole thing, like all the parameters, rotations and boosts, and they come over their Pauli matrices. There's the I in front of the rotations. There's no I in front of the boosts. Right hand side we'll do later. And then I define my lambda, the Lorentz transformation matrix, also with all the arguments. And this is just the exponential of the generators I just showed you, Jx to Kz with the parameters. The inverse Lorentz transformation, which is what we need here, it has a minus sign instead of the plus sign. And then here is the left-hand side. This is bar up, we want bar down, this one. So this is the left-hand side of what I want to show. This box, there is the conjugate transpose of UL, that's the U dagger, with all its indices. Then there's the sigma bar down with the index mu. And then there's the UL to the right with the same arguments. And the right-hand side is the sigma bar down with the inverse Lorentz transformation. And now, boom, I just have these two sides. Analytically, this is even too hard for my poor little computer, let alone for myself on the blackboard. But what I do is pick a random coordinate, 0, 1, 2, 3, pick a random angle in the range of -10 and 10, and all the other parameters, just some numbers, random, your call, and then ask left-hand side minus right-hand side, is that 0 or not? And so I execute it with some random numbers, and I get 0, 0. And since I always got 0, 0, I thought maybe something's broken in my code. I mean, it's easy to get 0. So I printed what is the left-hand side by itself, what is the right-hand side by itself, and you see it's non-trivial, and it gives you something. And you can run this millions and millions of times, and you get different answers because you pick random angles, and it's just always the same. So this was my quick test whether or not I got all the signs right. Yeah, and if you didn't, say we had messed up this thing, that up and down, we had a minus sign here. Just switch the sign of the spatial part, and then try again. It's not 0, 0. I was a bit confused. I thought, how does this matter so much? Because this is a sigma. I do this for every individual component. If I turn it around, I have a minus sign, there's a what? No, there is the sum over the mu's. So there will be a relative minus sign. So yeah, it's fragile. And when it works, then you can be sure that you got it right. So now this. What clearly has to work is to raise this index. So if I raise this now, I can write an equation that is a UL dagger sigma bar with an upper index, UL, where the upper index is just basically the eta, and we know what it does. It switches the sign of the spatial part. So instead of this, we have now with an upper index this thing, and that should be hopefully equal to the transformation with the lambda instead of the lambda inverse. And that's what I tried out here. So I have defined the lambda bar up, and then lambda bar up, that's this left and right hand side, and here is the capital lambda rather than the inverse, and I hope, yes, it works again. So that had to work because I'm just, here, numerical stuff, 10 to the minus 10, so that we call a 0. Well, yeah. I've also done the right hand side, but I guess you'll believe me, I don't have to. I need to do it for myself just to be sure they don't mess it up. Also, you just can't look into books because some have different notations, some use active rather than passive transfer, so there are minus signs everywhere. If you do a computation and you really rely on it, not homework exercise, but you really rely on it, then you have to do it all by yourself again. What does this help now? I wanted to. We get there. Now I have this object, right? I have, where's my bar? I believe this. I have this object, sigma bar mu psi L. Now I'm leaving out the first spinor. I'm looking for something where I connect the mu and the A. And the sigma is perfect because it is a matrix that mixes the two components and has index mu. So that has a good chance. So let's transform this under lower transformations. And now I only have one here, psi bar mu, UL psi L. And now I want to use what we just figured out. That's why we did this. This thing here is what I have there. And it is this side, but that's so I multiplied it with my dagger to the minus 1 left. And then this is equal to, this is gone, and then we have a lambda mu, then from the left, UL dagger to the minus 1.
Does this have to be on the left here, or like just like if we applied
What does it be on the left?
the U dagger inverse? Like has to be left of the lambda.
Yes.
Which is
No. It's very, very tricky, the whole thing. So these are just the numbers because they're the components, mu and u. There's nothing hidden, there's no matrix.
Yeah, I see.
Yeah. Numbers. This thing is a matrix notation, so that is a Pauli matrix. It's a 2 by 2 thing. So this, and that's also a 2 by 2 matrix, into the Pauli matrix. And so that can't go any further. And also I had to make sure to multiply it from the left because it had to catch this thing. Multiplying this equation from the right with the U dagger inverse isn't going to help because it won't reach it.
Yeah.
So the indices that disturb are the ones on the U's and the sigmas, but this one is innocent. So that's why I mean I pushed it through, but I can't push it too hard because there's the sigma bar. sigma bar, nu, and then from here to psi L. So I've replaced this thing by this thing. And now I don't know what this is. What is the Dagger inverse of UL? So let's write what UL was again. UL was e to the I half alpha k sigma k plus 1/2 eta k sigma k. By the way, the right one had this sign changed, e to the I half alpha k sigma k minus 1/2 eta k sigma k. Now here I want the dagger, so let's do dagger and UL dagger, which means complex conjugating and transposing. So the I gets minus I. This is real, this is Hermitian, alpha k sigma k, and that's all Hermitian. Sigma t. So what does this look like now? We have, like from here to here, we change the sign of the boost part, and from here to here, we change the sign of the rotation part. So looking across from there to there, both signs have changed. But both signs changing means what is e to the alpha in comparison to e to the minus alpha, whatever alpha.
I mean the inverse.
It's the inverse. So if I take the inverse, say from of this thing, it changes both signs, and then it's the same as on the left. So this is not equal. So the U dagger, write this down, UL dagger is U R inverse. That might come in handy later. And I can, of course, dagger the equation and take the inverse of the equation, and then the U dagger R is the U inverse L. That's the same thing. But still. Right, if I dagger both, the dagger goes away here and appears there, and then I take the inverse goes away and appears there. And that's this equation. Aha! So now I can replace this by well, actually, I spoiled. I think I spoiled the fun. I'm so sorry. I spoiled the fun. Or yeah. Maybe I can. Maybe you can just. Maybe you can pretend you forget about this, just that you don't know that. Because it doesn't really matter what this is. If I now hit this with the derivative, because all of this is constant, the derivative goes through to this. So okay. It's so still I know that psi L transforms into this thing, lambda. I might leave it outside even now, like you wanted it, and then so this is true. This is true. But then the D transforms into this. The D also has an index, so this goes with lambda bottom. The bottom is the inverse, right? So either you go like this, lambda mu rho d rho, and then all of this business is this thing here. U dagger L the -1 lambda mu sigma bar mu psi L, and then the derivative we pull all the way there. Here I'm writing this as lambda to the -1 and then rho mu, because it is what it is. And then there is this one first, lambda mu dagger L to the -1, derivative rho psi L, and these perfectly cancel, that was the point. This is a real upper index, this is a real lower index, so they have to, and they're contracted, so they have to disappear. This is a delta. This is a delta rho mu, which sets this to mu. Where's my sigma? Here, we got this. Sigma bar mu b rho psi L. And so they are contracted, and then we have this matrix that I figured out what it was. But can you forget it what it is? And then we have sigma bar mu mu psi. And if you have an equation that says this is 0, this is our proposed equation for the Weyl spinor, and that's satisfied, then it's also satisfied in the other system. It doesn't matter what's in front here. Yeah. If this is 0 in one frame, then it's also 0 in the other frame. There's the transformation in between, and the equation just gets multiplied by some non-degenerate matrix, and therefore that's 0, then that's 0, and vice versa. So we have an equation. In the next step, I will be more specific about this thing, but at this point, it isn't essential what this is, and I almost spoiled the fun. Now, it will still be useful in a minute. This thing.
First, before this transformation, yesterday in particle physics, we also transformed a field, and he said we should transform the differential because it's a local transformation. And now you also transformed that field, but you transformed the differential.
I see. I think when you say local, the local transformation, you probably did as what they call an internal symmetry, an internal transformation, which like local in the sense pointwise. If you have a derivative, you can't. This is not local. Then you have to have at least a neighborhood. See, I could. Later we'll do this. We have our field psi, and we transform it by the phase. That'll be the electric charge somehow. And so we have just the e to the, let's call it alpha, and nothing else. It's just a number. It's a complex phase. You can also do it with scalar fields. And then this psi L. And so this is what I would call a local transformation. The new field, let's call it the psi prime of x, is equal to this. The field at this x and this number in front. So then, how does this transform? The mu psi L, which is the derivative of this, so this will be e to the I alpha the mu psi L of x, and then I don't have a, I mean, there's not even a Lorentz distribution. I'm not pushing my coordinates along. Right? And therefore, is that what you did in?
Yeah, I think so. Yeah, we have.
Well, they said, oh, it's a local transformation. What transformation did you do?
It was a Gaussian of the quantum electrodynamics or something.
Yeah,
Sure.
that's what you transformed, but what you transformed it by, like what's the symmetry? And I'm suspecting it wasn't the space-time transformation, but this is space-time transformations, and so our x is changed, and yeah.
Yeah. Okay.
But we'll also do this in probably a week. but that's correct right there. And our proposed equation now is sigma bar mu d mu psi L equals 0. And this is called the left chiral Weyl equation. There you go. And you don't have to go second order in the derivatives because you have an index to play with. We can of course wonder, like we wondered before with other equations, is this physically sensible? For example, what about the dispersion relation? Let's go to momentum space and see what it does. Like, want to see energy and momentum related in the relativistic way. It will probably work because we have all these new indices, but what is it anyway? So momentum space. My psi L of x, I write this integral psi tilde L of p to the minus I p x h bar d for p. And then I act with this operator, differential operator, onto this field, and it goes in here, and it really only acts onto the x right there, like yesterday. So sigma bar mu d mu psi L x is integral. I don't know what to put, where to put this. It shouldn't go past this thing because this is my finger. This also has two components, just like this thing. So if sigma comes, it shouldn't go. It wants to go in this into the integral fine, but not past the sign. Of p. The derivative is okay. Then we get the exponential. And then the inner derivative is with respect to this x, and that will be minus I p mu over h bar. And like yesterday. The mu's are contracted between those two things. The minus I and the h bar is just decoration, doesn't matter. And then we can again use the independence of the different modes, the inverse Fourier transform, and conclude if this is 0, as our equation claims it, then in momentum space we have sigma bar mu p mu psi L tilde at p is 0. And I put them now together, there was no reason, but now the indices are next to each other, it looks nice. What is that now? Yesterday we said, we did the same argument for the scalar field, and we said, okay, if this all the product here has to be 0. And if this doesn't want to be 0, as both, well, then I guess this has to be 0. It's not quite as easy because it's a matrix. It would be enough that a linear combination of this is not quite as obvious. Let me do this. Let's disentangle this guy. Sigma bar mu b mu. The sigma bar was 1. Let's do this. Sigma bar 0, p 0. There it doesn't matter. And then we have minus sigma bar I p I. So with this metric here, this is explicitly in with I. Then this guy, if you look it up, sigma bar mu was 1 minus sigma bar. Because we started off with the lower one, and that was 1 sigma. Confusing signs. So the 0 component in any case is a 1, and then we have the p0, but p0 is e over C. Like that. And then we have minus from here, and then we have another minus sign from there. And then we have sigma matrix times, and that's just the P vector. Is now a good time to point out some pitfall, dangerous, like really deep in the notation? Maybe. And just so that you don't think it has anything to do with momentum space or what we're doing now with sigma matrices, it has always been there, but we haven't stumbled upon. If we say our x, so that's why I'm using the x notation. The x is of course and then x I. So when I write in some equation, maybe a side calculation, and I need to be specific about an index, and I write x I, then so let's say I write x3, or we also have x2, then this means it's the upper. I have to look at the contravariant one and then give this the value and then look what it is in this thing. And that is not the same as the one with the downstairs, like x0 minus x, so minus xi. But well, we can be, if you lower it, then this sign switches. But if you have a lower index, then of course you want to write this. So this is just the spatial part of this vector. So if I lower and raise the spatial index, I get a minus sign in our metric. But if you're kind of not thinking relativistic, then you always, at least I think, lower indices. For example, the Pauli matrices. The Pauli matrix has always been x, y, z, and it's always, or if it's sigma k, there was never a Pauli matrix with an index upstairs. So the normal index placement of these Pauli matrices is downstairs, and non-relativistically, my x vector is also usually I think of it as downstairs. But that's dangerous because the downstairs is really the minus version of the vector. This guy is the vector. So I'm saying the vector components of the momentum are the ones with the upstairs index. Had I looked at this, or even better at this, then I would have thought, oh, this is the downstairs one. So let's hope to not mess this up.
But the identity matrix, all right?
And here is an identity matrix, which people don't usually write lazily. Because what else could it be? If there's not, then it's an identity. It's identity in any space, in any other space. At first, you think that doesn't make any sense. It's like different units. This is a 2 by 2 matrix, and that's a number. How can you add them? You have to add them in this way, on the diagonal. We will leave this out as well, like all the other. So somehow. Now, very sketchy. Let's remember yesterday. Yesterday we had p squared phi equals 0. So we went to momentum space. The two derivatives turned into p squared, the 4 vector squared, not the second component. It's the 4 vector squared. And then we spelled this out, and this turned into p squared over c squared plus minus m squared c squared. Phi of p. What? P vector squared. This is what it is. And then we said, if this wants to be zero, non-zero, then this has to be zero, and then we had the dispersion relation right there. And naively, I want to do the same thing here. Mu on the psi L tilde, it's this thing, E over G plus sigma times E on psi L tilde, and that's zero. And I want to say, if this is not zero, then this has to be zero. But I can't just pull this out. I can't say the matrix has to be zero. If this wants to be non-zero, because this can be non-zero and in the kernel of this matrix, then it's a non-zero one. That can be also non-zero and I still satisfy my equation. So I have to turn this into a scale. Ideas? It's a bit like when you have your complex numbers and you have an x plus I y or so, and you want to make it real. How do you make this real? Like by multiplying it with, so what do I multiply this to make this real, obviously? With the mind.
That's not an x minus iy.
Yeah, it's called complex conjugate. And so here, this is at least what I'm thinking. Let's hit this equation with the conjugate of this. So this I'm multiplying by p over c minus sigma pi times, let's say sigma vector. So here's the minus sign. Let's see, right? Because I want to kind of get rid of this yeah, there's the matrix part. A sigma squared is the identity, if it all works out. So now if I multiply it, then I have p over c minus sigma vector times p vector, e c plus sigma times p psi l. And now I have e squared over c squared, these two together. These two together is plus, these two together is minus, and they do commute because that's just a number. So the plus and the minus go away. I only have the square of this, the product of these. So this is a minus sigma vector times p vector squared. All of it on this. And now the claim is that this guy is a unit matrix, proportion to a unit matrix. Let's look at sigma times p squared. Now, this is sigma in the upper index now, sigma I, I. And the summation convention. And then I have the same, again, I'm using the J, so not to have the double indices. And the P can move to the side for a second. Sigma I, sigma J, I, J. But the product of two sigma matrices you were supposed to remember, it is, let's try it out. What is it? Remember? Okay, do you remember? It's epsilon I J K sigma K. Let's write the identity because it's cool. And what's missing? I. Is an I missing? There. And now all of this is multiplied by P I J. The good news, if they're the same and this is intersymmetric, in I and J it disappears. The first one goes away. And the second one is the contraction. And this is P squared times identity. Aha. So then my equation here is P squared over C squared minus P of C vector, that's the spatial part, vector squared. You know, you gotta figure out your own notation that like where do you put arrows, where not, and So there's an arrow now, because if it is without, it is the 4 vector square, or the second component of the 4 vector. Psi L delta 0. And now this acts on both components. And if I want to have something in the first component, never mind the second, then I still have to have this with 0, or the other way around. So at any rate, I have this to be 0, and that's our dispersion relation. This equals 0, and then bring it to the other side, multiply by c, and then p is equal to c p vector, picking the positive value of the square root. You can also, I mean, on physical grounds, this e should be positive. It's a free part. It must be squares if you don't like it. But we see it's a massless particle. So our Weyl left-handed Weyl particle, satisfying this equation, is a massless relativistic particle. It's all good. Now solve the equation and see it propagate. We can, so once we figured this out, we can still go back before we multiplied. So I want to look at this equation again. We multiplied it with this sort of conjugate operator or matrix in order to figure this out. And now I know it, and I go back into the first order equation up here. And I have the e goes away. So let's write what I'm doing. I have e over c plus sigma minus p vector e L tilde equals to the series the momentum space equation, but I know that e is c p vector. And then this is just the p absolute value plus sigma times p on this. And now I'm going to divide, I multiply by 2 over the modulus to get this here and make a unit vector out of this. This is the p vector divided by modulus. This is a unit vector in the p direction. And the 2 is for the sigma. It was on it wants something like this. So I have 1 over 2 plus sigma half times p vector over p vector, absolute value, on side L. Now this is fun. Maybe you want to write this thing as p vector hat for now, since it's in chapter 4 classical field theory. Later hat will be an operator on some Hilbert space, and that would be makes no sense here. This is just a unit vector, and I don't know how to otherwise. I think I'll stick to this in the future, but for now I just have a unit vector. And sigma half, what is sigma half? This is the Pauli matrix half from like normal quantum mechanics. The Pauli matrix when you talk about angular momentum, it's the spin. So, and then this is a spin a half particle, then you have this S. So what this is S times P, it's the projection of the spin matrix onto the direction of the momentum. So it's like when you have your S component, this D component of the spin, and you have the spin vector times so the D component of your vector, and that is a half sigma Z. And here it's now projected onto the momentum. Your Weyl equation, this is the Weyl equation after 3 steps, but it's still the Weyl equation. And what does it say? It says 1/2. Let's bring it to the other side. It says S times P vector hat on psi tilde is equal to minus 1/2 psi L tilde. So that's also a very cute equation. It's not going to get the box yet because this guy gets a name. The spin projected onto the momentum, under the direction of the momentum, is called helicity. So this thing we will just define as H. We call it helicity. Now, if this is a particle that doesn't know where it's up and down, we don't want to talk about it has spin up or spin down, but it knows where it's going. And since our Weyl particle is massless, it for sure is going. How fast is a massless particle going? With a line. So this cannot even be addressed in any reference frame. It's always moving at the speed of light. So what's more natural for this particle to have a spin, talk about its spin with respect to its direction of motion, rather than an arbitrary z-axis. And that's what the helicity is. Helicity can be plus or minus 1/2, because it's a spin 1/2 particle. And on any direction, it's always plus or minus 1/2 the component. And here we'll just pick the momentum as the direction for the quantization of the spin. And the Weyl equation now says H equals minus 1/2, essentially, really acting on the side. So as a H psi equals minus 1/2 psi. This is one way of writing. Now it gets the box, right? This is your Weyl equation, momentum space, and there's no tilde over it. Exactly. And that's funny. Not up and down, not plus or minus. It is always minus. There's no choice. The equation says that. This equation that we came up with, and which is gone, but it's so cute. So this is what we came up with. Nobody says that this makes any sense. This is right, and this is physical or whatever. But it's a relativistic invariant equation of something that moves at the speed of light. It's massless, and it has a spin of 1/2. Why not? But it has only so if it's moving this way, the spin component is the other way. Right, so this is the S projected, where it is this. Maybe you want to call this the ST or something. And it's going the other way. So your Weyl equation says it is a spin 1/2 particle, which rotates basically backwards. Particles, now you can have other particles. You can have vector particles, so something with spin 1 and more. And you can always ask what is their helicity, just the projection of their angular momentum on the momentum. And if I'm right there, if H is less than 0, we call it a left-handed I'm reluctant to say a left-handed particle because it's not a property of the particle by definition. It is really a left-handed state. Not in the sense of quantum states here, but in the sense of it's doing this right now. Like I am now, say, left-handed because I'm rotating in that way. But I can, at another day or another moment, become a right-handed person. I can go around. Or even if I go left-handed with respect to you, you're crazy, you go faster than me, so it looks to you that I'm going relative to you in the other direction. So I can be left and right-handed for different observers. The handedness, the helicity, is a priori observer dependent. Here it isn't, because it is always a partition goes, but I'm massive, literally, and this is massless. There's a difference. If you want to see this spin the other way around, you have to basically go faster than it. But it's already the fastest thing there, so you can't pass it. So therefore you can't see the other. So you can't. In this particular case, the left chirality is the same as the left-handedness. That's right, left-handed state, and you know what I mean. So, and thank goodness, people call the left chiral Weyl spinor the left helicity, so the left-handed state. So it's left-left. Since these are independent concepts, some person could have come up with, let's call H, let's do right-handed, right? Then the left chiral spinor is a right-handed. I'm just saying they're a priori independent. The chirality is, how does it transform under Lorentz transformation? Do you have to put a minus or a plus sign in front of the boosts? And now this thing is the projection of the spin onto the direction of motion. And while the representation is what it is and always stays the same for all the observers, it's just how it transforms. It's a property of the particle. The helicity could be observer dependent. So it's really something different. The equation of motion here is so special that it links the two. For a while, spinor, it is the same thing. And therefore, if you read something, then people, maybe they even say it's the same, isn't. And then, even worse, since this is both, so here you have the concept of chirality, and here helicity. And now you call something here left-handed, like whenever in lecture, I don't know when, last week, I did call the representation here left-handed, and here it is called left-handed. And when it's not the same, then it's a question, which one, where do you keep the handed? So to be on the really safe side, you don't use every handed and stick with chiral and left helicity. I've seen that too. And then you don't, then you got rid of this confusion, because you never say handed, and then you don't, and depending on who you talk to, one might think the handed is this, other handed is this. The more standard, I think, more references call this the handedness, even like the real particle physicists. So this is standard way, but be aware that some people call the left chiral left-handed because of the fact it's linked here, but it is a different thing. So I for myself will, for the distinction of with representation, stick to the word higher. Now we've learned something here. And H larger 0, 1 we have, it's the right-handed state, and it can change. Like it's observer dependent, and your equation of motion might say it doesn't change, it's conserved. You might have an equation of motion that changes your chirality. It's not this one, but like your spinors that we will have, then they can actually change. Yes.
How should we think of like spin when we're not in quantum mechanics, like when we're still in classical? Or is this just like, let's keep this for later once we?
Yeah, I think that's what it is. Yes. Right. This is a little good point. Yeah. These fields, I mean, I'm talking about classical fields and here it all works. But next week I want to start with the Lagrangian. I mean, Lagrangian classical field theory, just that, no quantization yet, and derive these equations from an action principle. Because you do this because you have more power then, you can find out conserved charges and all this. I could also stare at the equations and transform them, but it's nice to have this action principle. And then you'll see you can't derive this from an action principle with, well, actually this one, yes, I'm about to add a mass term and you can't, unless they are anti-commuting. And that's also departing from the classical world. Like it's not a normal electric field or so. It's something weird. It's a so-called Grossman value. It's just anti-commute. It's going the direction of weirdness of quantum. And I guess the spin a half is really linked to it. All the half integer ones are the Grossman fields. And so yeah. It's strange classical. But I'm not doing something weird. It's just that I gave a name, hinting at what will come, as you pointed out. This is a Pauli matrix, and this is a 2x2, this is a 2x2 thing, this is a column. It is all well defined. It's just that when we go, when we are, it'll be that eventually. Very good. We can do the same story now for the right-handed particle. And then for the right chiral, damn it. I was going to say for the right chiral, here I have representation. And of course you have to do it to figure out where is all the changes, but they're so boring. I'll give them to you. The first thing you have to know this if you are beggar, and then well you want we want this thing here. Psi r beggar psi r psi beggar r sigma vector psi r, and figure out what kind of vector this is. And the answer will be given if you know how this guy transforms, and it's a lambda mu sigma mu if you define this thing as one sigma. And you can lower it, and then the lower one transforms with the inverse and has one minus sigma, because you lower it, the space bar gets a minus sign, and then you find that sigma without the bar, mu d mu psi r is your equation. So this, and do you remember what the others were? Like sigma bar mu was 1 minus sigma. You know how I remember this? At least try to. So the bar, it looks like a minus sign. And the upper is for me more natural because we also started with x upper mu. It's kind of the more natural, whatever. It's a little contrary, but still, I'm trying to convince myself it's more natural. So in the more natural placement, the bar is this minus sign. And here in the more natural placement, there's no minus, so it's a plus. There's no minus, it's plus. So this is how, and then when I want to know what is the one without the bar, but lower, I have to remember, oh, the one without the bar upper had, no. So this is how I try to remember the things. And the left equation was this, mu psi L. And here it's just no bar. And the difference is this minus sign. So how the time and the space are mixed together there. And if I had put a bar there, just this poor little minus sign, this equation wouldn't make any sense anymore. If you transform it to a different coordinate system, then it just messes it, and it won't be the same. It relies on this thing, and if you don't have every signs in order, it doesn't work. So this is the equation with this definition for the right-handed, for the right chiral field, and this is the equation for the left chiral field. And now when you do the momentum space, of course, we do the conjugate. Oh, by the way, you know what the conjugate is? Here, I first split it into time and space. There was this E, and then it was the vector part. But and then we turned around the sign there. The other one is just this, right? So what we've done before to get the dispersion relation was multiplying by basically by the other. So we did this, we get the sigma times well, it's this, of course, sine tilde r, and then you pull this apart with this different relative sign, and then in the end you get the same h sine r with plus a half. So this is your tilde chiral equation in momentum space. For the right hand, and it says the right chiral field is also a right-handed field because its spin is always in the direction of the motion. Okay, this is a column. Are you kidding me? I don't know. Now it's at a mass. Try it at a mass, make this thing massive. And remember, as a guide, what we did for the scalar field. Scalar field, we had our three. What am I saying? The masses equation, and we just added number 5, and then working out what the dispersion relation now is, we fixed all the constants, and it turned out to be m squared c squared over h bar squared, and boom. Now here, going into the left chiral sector again, we have this equals 0. And now, how about trying this? Just like that, and figure out what the number is. What do you think? And this is the highlight, I think, of today. I guess there's it's just the mass sitting there. I guess it will be the mass. Really, what I think, it'll just be mc over h bar rather than the squares, because this is the first order, and then we have to hit it with this the second time, it'll be squared. So it looks very convincing that this is going to be, let's call it k and figure out what it is. But doesn't this look convincing? See, I have tortured you last week and this week, I mean, from the beginning of the term, but particularly last week, with all these representations and e to the whatnot, and you thought, oh, okay, fine, whenever I'm going to need it. Here, this equation looks so innocent, it looks just the same, it has to work. But since we know now a lot, we can immediately say it doesn't make any sense. Because how does this, that's why I spoiled it, I left it here. How does psi L transforms under Lorentz situation with the UL psi L. And then here we looked at it. We looked at how does this left-hand side, that's this guy, with the derivative, how does this transform? Shall we do it again? So how does this left-hand side transform? Psi mu d mu psi L goes to, we can recover a little bit. If this, the difference is the derivative. I have to add another derivative. Oh, maybe I did this somewhere actually. Yeah, we did this before. If you remember, it was the dagger. And we worked out what this was, but then I said we don't need it. And the rest was okay. It was this thing, mu d mu psi L. And that's it. Remember, we derived this before, and we said if this is now the equation, this equals 0, and setting this 0, then we have it in the other transform system as well. No, never mind what this is. Now, I would have talked about what it really is. Now I need to know what this is, because I'm adding it to something else, and this something else transforms with UL. So if this equation with the plus wants to make any sense, then I have to have the same transformation, because I want to factor it, right? Now, if this goes in here, I want to factor it to have the same equation. But I can't factor it if this is something else from that. And now we know it's something else. This is UL inverses UR. So the left, this term transforms with UR. The business with the sigma here turns the left chiral representation into a right chiral representation. And therefore I can't add psi L to it, although it looks nice. And this was the highlight, because now you see that it's kind of worth it. Worth it. Also worse, yeah. But how do we fix it? Can we put a mass? Can we put a term that transforms in the right direction, in the right representation, the right chiral representation? Can you build out of IL something that transforms in the right chiral representation? If you did your homework, remember your homework? There was something. What was there? Exactly. So that's the reason why you did this on the last homework. If psi L transforms with UL, then sigma 2 psi L complex conjugate transforms with UR. I don't want to repeat this, because it was a homework exercise and you have the solutions. You use that sigma 2, sigma, any other, sigma 2 is minus sigma k star. It's just an identity, and then with the sigma 2 business, we can deal with the star. And this minus sign flips it just in the right way, so to turn the UL into UR. This, if you transform UL here, then you end up with it. If you transform psi L, and you have a UL star, this sigma with the UL star takes away the star, but also gives it a minus sign so that this comes out. It is plausible, and you showed it. And that's perfect. If this combination transforms with UR, why don't we just write sigma bar mu psi L plus some constant sigma 2 psi L star equals 0 as a proposal? Looks more ugly, admittedly. Sigma 2, what's that star? But this has a chance of working. And now I'm going to do the same thing as before, getting the dispersion relation. We knew kind of how this worked. We have to we have to square this thing basically. But with the sigma mu d mu without the bar. I'm acting on this, and then it will be something nice here. Let's do it. Well, what is sigma mu d mu sigma bar mu d mu psi L? So this is sigma mu sigma bar mu, and then d mu psi L. I have pushed the derivative there, nothing weird. Now I'm adding the same term again, sigma mu sigma bar mu, and divide by a half because I can't just add stuff. But now in the second term, I'm going to relabel the indices. What was mu? I will call mu. And what is mu? I will call mu. Now I have to be careful. I can't just relabel it here because this one wants it like this. However, derivative they commute, so I can put them back. So this is not, it's not relabeling. I relabel it. Now I'm just pushing it. So I can just turn them in the other order. I'm doing this because I have to do this explicitly, and it's nicer to have a symmetric combination of these things rather than just a single one. The single one contracted, the single one will give me many terms. Then I contract them with something that's symmetric in these indices, and in many terms, half of them will go away. If I from the start look at the symmetric combination here, I don't produce all these terms, so that's why it's easier. So I want to know what this is. And then let's do it. We have to just do all the combinations, right? 0, sigma, 0. Sigma 0, 0, bar. Plus sigma 0, sigma bar 0. These are just identity matrices, right? This is 2 times the identity matrix. 1. Then you have sigma 0, sigma bar I, plus sigma I, it changes, and then sigma 0, and bar. This is an identity matrix. This is up with a minus sign, so this is minus sigma like that, right? Plus, now this is the sigma I, this is sigma I, and this is the identity matrix is 0, so that makes 0. So for this one is 0. Now we have sigma I, sigma bar, oh, this is boring, this is that term. So but let's write it, we don't have to compute it. Sigma bar, sigma I 0. So the opposite order, but the opposite order is literally that, because this term is this one, this is this term. I don't torture myself. And then we have a sigma I, sigma bar j, plus sigma j, sigma bar I, and that is now a sigma I, of course. This is a minus sigma j. This is plus sigma j. This is a minus sigma I, but we know that these are the epsilons, but it's antisymmetric, the epsilon, so in the sum it goes away, that's the term I was talking about, it's just the delta part, so it's minus delta ij identity, and this is the thing, boom. What's that? And then we write this as two eta ij, and the minus signs in this metric, and then we write this as two eta 0, 0, 1, and then we have a formula that says sigma mu sigma bar mu plus sigma mu sigma bar mu is equal to 2 times eta mu energy. By the way, the very same thing holds when the bar is on the front, but you have to do the same. It's in the computation. Now, and going back here, this is 2 times eta mu times identity. The 2 cancels, wonderful, so we have box psi L. So this thing's together is the box. But now this will also end up here. So we have box psi L, then there's this K, now comes this other business, the sigma mu, and then there's a sigma 2, and then there's a D mu psi L star. That's equal to 0. That's what we have. Now I need to know something here. But I have an equation, basically I have an equation that knows what the original equation knows what the derivative on psi L is, except for the complex conjugate. So I'm going to use this equation and complex conjugate this equation, and then try to put this in there. So let's go back here to this equation. I don't know what to say. That's the original proposal, right? So here, that equation, complex conjugated, is sigma bar mu complex conjugate d mu psi L complex conjugate plus k complex conjugate sigma 2 is imaginary, so then minus sign, and then it's a psi L equals 0. That's the equation, and I want to use it here, but not the same. However, the sigma 2 does something fantastic. I'm going to multiply this equation from the left by sigma 2. Then I have sigma 2, sigma bar, mu star. While we're at it, I'm inserting here. Here I want to insert 1, which is sigma 2 times sigma 2. And the sigma 2 is sigma 2, d mu psi L star minus k star, and these two turn into 1. And now this you have to compute, I guess. If I had time, or if I could keep it, then I would compute it for you, but it is equal to the sigma bar. Yeah, it's the sigma. Let's see. Sigma 2, 1 minus sigma vector. The 1 star, you don't even see that, and then this thing. So then it's sigma 2, and here it is minus sigma 2, sigma star, sigma 2, and then I say we're supposed to remember this is sigma. So it is 1 comma sigma, and this is just the sigma mu. And this was the sigma bar. So they turn into each other. And that's good news. Um, The equation on top is box psi L plus K sigma 2 sigma mu sigma 2 d mu phi star L equals 0. But this equation here says that right, it's sigma mu sigma 2 d mu psi L star is equal to K star psi L. That's this equation there, and that's perfect because we can use it right there. Is equal to, you get my minus signs right? K. K star psi L. And so the whole thing is now boxed psi L plus K squared psi L. And in momentum space, this is minus P squared over H bar squared. And that's just K squared. And if this is supposed to, and that's supposed to be 0, what do we have to put for K up to value? So P squared, the 4 vector squared, is just M squared C squared. Didn't we have this somewhere? Remember that? Let me see this. So the 4 vector squared is P squared over C squared minus P vector squared, but this is blah blah blah, and then you get M squared C squared. So this is M squared. So our K vector K squared is M squared C squared over H bar squared. And so the K is up to a sign MC over H bar, and really just if even if phase could be kappa, it could be anything. It's called kappa because it's a K. We don't know. We don't know. We just knew this thing. And so our equation for the massive Weyl spinors is this. No. Box. No. Going back before the application, this paragraph, and this is the equation with K, we know what K is. Sigma bar mu psi L plus this K MC over H bar EPI kappa sigma 2 psi L star equals 0. There it is. And now this is ugly. Can we fix it? No, because we can always redefine what we mean by psi L. This is your expertise. You can just define whatever phase there, just redefine it. And since here is the psi, and there's the psi star, they rotate with different phases. There are 2 knobs, and here's one, they're kind of off, and you can turn it. So say this is 10, e to the I 10. I'll just dial this thing by what? 5, I guess. If I dial this with 5, then I get a 5 here, and I have the 10 there, and I have a minus 5 there. The 10 and the minus 5 gives a 5, the same as there, and then divide the whole equation by e to the I 5. So I can get rid of it. This one is just inessential, without loss of generality. We can throw this out because we can just redefine it. And now this is your equation, but I can't put a box because it's out. And it's the very same thing without the bar in R for the massive right chiral. Yes. I'm basically done, but I want you to ask one question. I thought you would ask this question. And let's pretend you asked it. Like there's the sigma mu. This is one and sigma vector. And then there's the sigma bar mu, which is the one sigma, right? What's your question?
Why do we use these, like,
Why so much, right? Why not sigma bar mu? It's literally the same thing. Everywhere I write sigma, let's say get rid of the bar. We don't like the bar. We can get rid of the bar by always writing this thing. You just have to switch the index up because the down is this with the up. So if you don't like the bar, and since we have another one, we can write this equation as sigma mu e mu psi L, and it still is correct. It's absolutely correct because it is the same thing. But now show this someone outside. He's going to yell at you. Why?
or indices?
Because it's not manifestly Lorentz invariant. This object without the bar and lower index transforms contravariantly, and nobody would have guessed it. Because you put down, and that's why you need it. It's just really different things. All right, so therefore we just don't do this, and this is like the numbers are the same, but you wouldn't you know which one to write because of the. Okay, so now I answered your question that you didn't have. Thank you. More questions that you don't have or that you do have? Well then,
Repeat the last part again, where you get rid of the POI kappa.
yeah, so let's do another example, not e to the 10. This is a phase, right? It could be a minus sign. Let's say this is just the absolute value, since this could be complex, you could have any phase, but let's just talk about plus minus. You don't know which sign we get, because the dispersion relation only asks that the square is this. So we have a sign that is plus or minus there. And I'm finding I can adjust it. If you have a plus, I can make it a minus, or if you have a minus, I can make it a plus by changing what the sign is. If say you have a minus sign, and I really don't like minus signs, then I go, okay, my new sign, mine, how do you get mine? Mine is yours with the eyes. It doesn't change much. It's just because I can multiply it frequently. But then my side star will be minus r. And now if I insert it here, then I have mine. With the mine, I guess I have to bring this out on the other side. So I have a minus I here, and this on the other side. So I have a plus I here, mine, and then a plus I here. And now I multiply through with I, and that goes away, and that goes away, and I have a plus. So by redefining the field, I can switch the relative sign. And I can even do it with a phase more than a sign. Just I have to do always half of what you want to get rid of. There was e to the I10, and I had to redefine by e to the I5. Here I want to the minus sign. The minus sign is an I. Half a minus sign is an I, right? Because I times I, the other half is mine. That's not essential. Doesn't change anything. Okay. Well, then enjoy the weekend.